Good morning, everyone. Welcome to this new webinar by the International Energy Agency, still in our energy data and modeling capacity building program for Nigeria. I'm very happy to be with you today and to continue our journey on understanding better the how to do energy modeling and to develop long-term plans on energy. So I hope you had a good Haile Lada celebration and holiday, and that you could enjoy those days off. After the session we had on Monday, which presented the basics of energy modeling, today we will look at one side of the energy system, which is end-use sector, to try to understand the demand for energy, looking very much into details at what do concretely people want, and we will focus on the building sector. So building means residential plus services. It's an interesting sector because it involves all the energies. We need electricity for buildings. We need oil products. We need gas. There is a lot of bioenergy as well, and there are very diverse needs from cooking some meal to using electricity in appliances and to many more usages. So just showing you again where we fit in our overall agenda. This is the number 2 session on energy modeling and looking at demand. Tomorrow we'll discuss power, and on Monday we'll discuss primary fuel supply with hydrocarbons. As for previous events, it's virtual, so any urgent clarification, please raise your hand. Feel free to ask your questions all over the presentation, and we will have one break at the middle and one time at the end to address and to answer all your questions. And as usual, I'd like to start with a few Menti questions, just showing you before the agenda for today. So we will set the scene on the building sector globally and in Africa. We will discuss to you a bit activity, structure, and performance in modeling in this specific sector. We'll discuss drivers, which is an important item when we do energy modeling. And then we'll really go through the entire process from understanding future drivers for future trends, to estimating useful energy, allocating a portfolio of technology and fuels that can address the needs for services, and then estimating what is the final energy demand at the scale of a country, for example. And as mentioned, I would like to start with asking you some very quick polling questions on Menti. So I invite you to connect to www.menti.com and to use the code for today, which is 40417757. So I give you a bit of time to connect. So the question we are asking you is, if we look at sub-Saharan Africa today and at the residential sector, according to you, what is the largest fuel which is used after traditional biomass? Why is that? Because traditional biomass is by far the #1 fuel used in the residential sector today in sub-Saharan Africa. But if we look from number 2, which fuel would that be? Would that be electricity, oil, gas, coal, modern use of biomass, or solar thermal? So the code that you may be able to see in the top part of the screen is 40417757. I'll write it in the Q&A too. So again, this question is looking at sub-Saharan Africa on a whole. Maybe for such question, the answers would be very country specific. In countries such as Nigeria and other oil and gas producers, it's very possible that oil gas would have a large share of the energy consumption in the residential sector. It can be gas through network. It can be oil under the form of LPG for cooking, or oil under the form of diesel for backup electricity generating systems. So these are indeed some fuels that would be highly used in some countries. The right answer is electricity, and you voted right for that. As this is the number one fuel used in the residential sector after traditional biomass. So thank you for your answers. So this was the situation for today. Now, I would like to ask you, looking ahead, what do you think will be the first fuel in terms of growth? Which fuel would you expect to account for the majority of final demand growth in the coming decades? And you are proposed the same fuels as just before. So in terms of projections, which fuel would you expect to account for the majority of final demand growth? So which would be growing most? Um, okay, I could not see the answer, but no, that's okay. So you're voting mostly for electricity and solar thermal, whereas coal would be the least rated. So we'll look at those questions at the perimeter of the world, sub-Saharan Africa, and a bit on Nigeria too, based on the modeling we've conducted. So I don't give an answer now. We will see in a second in the slides. But very interesting that you see electricity, gas, and solar thermal as the main one. We'll discuss that in a second. Thank you very much for your answers. I'm coming back to the presentation. So, giving you some insights from the IEA data collected on the building sector. So these are historical trends in terms of energy demand as well as CO2 emissions from the building sector. So you can see that the building sector has a very diversified mix of fuels, all the energies are used: coal, oil, gas, but also electricity and bioenergy. This is a picture globally, and these were the historical data. So we see that energy demand for buildings has been steadily growing over time. You can see that bioenergy, the green share, has remained stable, whereas other fuels such as electricity have increased much more over the period. Now, what could the future look like? Again, we need to take a scenario approach, and here, considering the steps or stated policy scenario, so announced policies and known technologies and investment plans, this is where the world could go. So we would expect a smooth or linear growth in terms of total energy demand. And when we look at the mix of fuels, we would see that fossil fuels like coal and oil are set to decline. Gas would grow a bit, but the total amount of fossil fuels would be quite the same in 2050 as today. On the contrary, electricity consumption in buildings is set to almost double in the coming 3 decades. So we expect electricity to be the number one and the fastest growing fuel. But then there are also other sources that would also grow as a result of the increase of electricity and relative decrease of coal, oil, and gas. We would see emissions flatten. This is the yellow line that you can see on the top part of the screen. So this is under steps scenario, but a different future is possible. And this is what it would look like under a sustainable development scenario with universal access to electricity and to clean cooking, and with climate-driven objectives aligned with the COP21 Paris Agreement. So you can see that the CO2 emissions would sharply decrease, and this is due to a phase out of coal and a strong reduction of oil and gas at the benefit of electricity. What we would also expect here is much more energy efficiency to be able to do more with less energy. So these are some prospects at the global level. Now, looking a bit at projections for Nigeria that we had conducted in the World Energy Outlook 2019, and if we look again at the final energy consumption in Nigeria, so here you have all sectors, residential, but also transport and industry or productive use, and you can see that fossil fuels on the left are represent a very strong demand or strong share of final energy consumption in Nigeria, mostly for transport. So it's mostly oil products for vehicles. On the contrary, electricity is a way smaller share, and it's mostly for residential, but also for the industry. In the future, we can see that there is growth everywhere. In the steps, we have an almost doubling of levels. And if we look at the Africa case, there is even more growth in the final energy demand. And the difference between those two scenarios relates to, in Africa case, everyone has access to electricity and to clean cooking. There is higher GDP, but there are also efficiency gains which limit the growth. And for the residential sector, you can see that we expect energy final consumption in the residential sector, so the green bars, to be mostly met by electricity, but also a bit by fossil fuels, which can be LPG for cooking or diesel for backup generators. Looking more specifically at the issue of cooking, based on the data we have collected and we are working on with WHO, the World Health Organization, we observe that today most people in Nigeria are still relying on solid biomass under traditional use, so something which is not considered as clean cooking. By the end of the decade, this number of people would decrease, and we will expect more people to be relying on LPG, on improved cook stoves, as well as on other clean technologies like electricity, like biogas. But this will still let many people relying on basic charcoal stoves or traditional use of biomass, coal, kerosene. And again, under our Africa case, a brighter future is possible with everyone having access to clean cooking equipments and fuels, again, including biomass, improved and advanced cook stoves, LPG, as well as electricity, biogas, and others. Okay, so now this was about Nigeria and sharing some findings. Now we'll come back to really the fundamentals on energy modeling for an end-use sector, which is the residential sector. So really, what questions do we want to answer when we develop energy models for the residential sector? How do we start working on it? How do we develop assumptions? How do we make calculations? And what process can we follow if we want to go from what do people need, what do people want, to what energy needs to be provided to them to match their needs. And this takes into consideration the equipments or technologies that are used. This takes into consideration efficiency levels, but also behaviors and needs for services. I see there is a raised hand by Dr. Zarma. I will try to give you the floor. Oh no, it's maybe it was a mistake. Okay, so let's start on this part. You will hear from my colleague Tim and Ariane, who will also join at the end for the final Q&A.
On this slide, you have the general schematic overview of the world energy model. And in this presentation, we will focus on the building sector, which includes the services and residential sector, which are encircled in red on the slide. You can also see the main driver of the related energy service demand. When looking at this overview, we should not forget that an important additional feedback needs to be considered: the impact that electricity and heat prices and fossil fuel prices have on end-use demand in general, and in this particular case, on the energy demand in the building sector. When working on the sector, the first step before doing any modeling is to analyze what do people want. What they want and use are called energy services. In the building sector, it can be space heating, cooling, lighting, cooking, etc. To meet service demand, we need energy, and this energy is consumed by different technologies. In the building sector, it can be air conditioners, light bulbs, radiators, etc. And for each equipment, we also have its associated efficiency. We therefore can distinguish three areas: activity, structure, and performance. The activity is linked to the energy services. The structure is linked to the type of equipment present in the building sector, and the performance is linked to the efficiencies of the different technologies. And all of this needs to be depicted in the model. If we look in more details at the structure of the building model, we see that we have different parts that make up the model. The first part includes all the inputs that are needed to do the modeling: historical data, regarding energy balances, building stock, equipment sales, and also socioeconomic data like population, electrification rate, or GDP. And we also do some assumptions for the evolution of some of these data, so for instance, population. Some of these inputs will be used to compute energy service demand drivers, like household occupancy, floor area, or appliance ownership. Of course, these drivers will differ for each subsector. Indeed, the drivers are then used to determine the future useful energy demand, or the activity, as mentioned earlier. So for instance, for space heating, we can use the floor area as one of the drivers. In addition to that, we also need a number of historical and future technology data that describe the structure and performance of our system. These data include the efficiencies, the lifetime, the market share of the different technologies. We can then compute for each end use what technologies will meet the service demand, and we will finally estimate the energy demand by subsector and by fuel, as well as the investments and CO2 emissions. If we look in more details at the structure of a building model, we see that we have different parts that make up the model. The first part includes all the inputs that are needed to do the modeling. As we've just seen, we need a lot of data inputs, as data are essential for energy models. Accurate balances are the basis for all modeling work, as we have seen and mentioned in the previous webinars on energy statistics. That's why it's important to build a data repository to organize all the data that you will use for your modeling. As mentioned, the data include energy balances, technologies data with efficiencies, costs, but also policy data that will impact the evolution of this sector. We will explore which are the most important ones in the next slides. As mentioned earlier, one important step of the modeling process is to define energy demand drivers, as they play a key role in describing energy consumption patterns in energy models. Thus, it's crucial to define the best proxy to describe past trends and possible future ones. Before looking in detail at drivers and different methodologies to estimate them, you can see here the general structure for modeling end-use sectors. So first, with the drivers and econometric analysis, we estimate the evolution of the energy service demand, or useful energy. Then, to meet the service demand, we allocate different technologies. And in the case of the world energy model, we use a cost-based approach to do this. Then, with the efficiencies of the different technologies, we can compute the final energy demand. If we go back to the drivers, we will look over the next slides at possible methodologies to identify the best proxy for each subsector. The projections of activity variables can be based on regression with respect to GDP or electrification, but we can also use different types of curves, like the S-curve. And as mentioned earlier, this requires to use different data that can come from the IMF or other national reports.
You've now been introduced to the importance of buildings energy demand modelling and the strong role of bottom-up modelling of energy demand for each end use within the building sector. And then following this, the processes and structure used in the modeling of buildings' energy demand in the International Energy Agency. And now I'd like to focus in on one of the most important steps of our modeling process, and that is the definition of the best proxy to then describe the activity variable that can help us understand how service demand evolves for each type of building end use. So again, the proxy is the link that helps us to go from socioeconomic information to activity variables and then to services demand. Now, why do we need this link? Well, firstly, activity variables. We might have this information available for certain countries in the historical period, but we don't have it available for all countries over all of the time series, and we definitely don't have this information available for the projections. So therefore, it's up to us to take the information that we do have, and that is socio-economic information, and to use this information and these assumptions for the future to calculate our own activity variables. Once we've calculated these activity variables, we can use them in our projections to understand how service demand evolves, and then based on what technologies we choose, how energy demand evolves in our projections. Now, there are several types of activity variables that are of interest to us. Certainly in the building sector, one of the most important activity variables is household occupancy. So this is how many people live in each household on average. Now, household occupancy can help us to understand energy demand for end uses such as cooking or water heating, for example. Now, because we do not have information on household occupancy into the future, it's up to us to try and define a relationship, a variable that we do have information in the future, and this household occupancy variable. So here we've chosen to plot values of household income against household occupancy. So we've taken all the data on household occupancy that we do have for historical periods for different countries, and we've put them on this chart against the GNI per capita, which is in itself an indicator of household income or of personal income. And what we can see is we have an inverse curve that's being drawn here. So that means that as we increase the average income per capita or per household, then we are decreasing the number of people per household. So here we're seeing a strong relationship between GNI per capita, so gross national income per capita, and a decreasing number of people per household. So we have on the right an inverse curve equation that can be used to define this relationship, and then can be very interesting for us and is a key step in our modeling to be able to say in the future, if from our external assumptions, which for us come from organizations such as the International Monetary Fund, the World Bank, and our own assessment and projections of economic growth and population, we then use these assumptions on economic variables to understand via this equation how household occupancy evolves in time. So that's just one example of this process of identifying a proxy that has a good relationship with the variable that interests us and using this proxy to describe the activity variable. So here, household occupancy. Now, another example of a relationship of interest to us in the building's energy demand modeling area is ownership variables. And so how does the ownership of a given appliance, such as a refrigerator in this example, evolve in time based on another variable? So here we've plotted ownership of refrigerators for all the countries for which we have data and over all the years for which we have data. And we've plotted that against here where we have a discriminant criterion, but we can very easily say that we can plot this against GNI per capita or even GDP per capita. So the most important variable to have on the x-axis is income in this case. And if we build this chart and fill out the data, we can very clearly see that there is an S-curve relationship between refrigeration ownership, so the average number of refrigerators per household, and the average income. And so that means that with time, as income increases, then we get to a point where the number of refrigerators on average per household starts to really increase. And then as we get to a point where households are increasingly rich, then the growth in refrigerator ownership slows down. because once we get to a point where we already have at least one refrigerator on average per household, then obviously there's less need to increase and to continue to purchase additional refrigerators. So there is a saturation point, and that's why S-curves are so important, because they show us at the start that we might not have enough income even to think about buying a refrigerator, but at a certain point we start to cross that threshold and a refrigerator becomes a desirable and useful purchase and use of income. So we see that growth, that increase in the rate of growth of the S-curve, and then it flattens out as we start to saturate. So the S-curve is a very important indicator for understanding the relationship between many economic variables and the activity variables that interest us for buildings energy demand modeling. And I'll get to a description of the discriminant criterion and how we can draw upon several economic variables to influence and describe this curve in just a minute. But firstly, I would like to go through an example of air conditioning ownership. So here we've done the same thing as in the previous figure. We've plotted on the left-hand side, on the y-axis, the ownership, the average ownership of air conditioners, and on the x-axis, the income, the average income per capita. So we've used all the data points that we have in our database, and we can see that it's a big cloud of points without a very strong relationship. So here it's difficult to imagine an S-curve describing the evolution of air conditioner ownership with income. But when we bring an additional piece of information to the picture, we start to see much clearer relationships. So now we start to plot data points, so air conditioner ownership and income, depending on the need for cooling in that region. So here the need for cooling is described in terms of annual cooling degree days. So a cooling degree day is a variable that can be calculated based on the threshold temperature in a given country and the average daily temperatures within that country. So here we can clearly see that for countries in darkest red, so the countries with the greatest cooling demand need, there is a relatively strong view of an S-curve that evolves in time. So we can see that as in those countries, incomes start to increase, the rate of air conditioner ownership rapidly increases and moves towards one. So an average of one air conditioner per household. However, if we look at countries in blue, so with very low cooling needs, then we can see that even when incomes, average per capita incomes increase to very high levels, the air conditioner ownership stays quite low, because obviously these households, despite their high incomes, are prioritizing purchases in other needs because their cooling needs are not very high and not very pressing. So the message here is that sometimes we might have just the economic variables, so GDP per capita, and some information on ownership, but that's not enough to define a clear trend and a clear curve that can be useful for us. So sometimes we need to bring additional data to the table to help us understand the evolution and the relationship between the economic variable and the activity variable that interests us. Now, before going on, I'd just like to summarize some of the key end uses that we model in a bottom-up fashion in our buildings energy demand modeling, and the activity variables that we use to describe the energy service demand for that end use. And then further on, the proxy that we use, so the economic variable that is a key variable for us to help to understand the relationship between evolving economic conditions and the activity variable. And then finally on the right, the type of curve and the type of equation that we use to connect the proxy with the activity variable. So firstly, with cooking, the first curve that we saw was an inverse curve. And so for cooking, we use people per household to help us understand the evolution of service demand. So people per household is our activity variable. And as with all end uses in buildings, we're using GNI per capita, or you can use GDP per capita as well, as the most important proxy to help us describe the evolution of the activity variable. So we take our projection of GNI per capita that comes from other assumptions. So again, it might be World Bank, IMF. For population, it might be the United Nations. And then we use this variable via the curve, so the inverse curve in this case for cooking, to describe people per household and understand the evolution of people per household in time. For lighting, we use an S-curve because the activity variable is floor space per household. And with an S-curve, that describes the fact that as households become more rich, so does the floor space of those households increase. And then we get to a point where there's saturation, and so the S-curve starts to flatten out. For water heating, it's again a question of describing energy service demand by the number of people that live in the household, because if we think that each person in the household may take 1 shower per day, therefore the energy demand need for water heating is dependent on the number of people in the household. So here, again, we're using an inverse curve, the same as for cooking. But then if we look at air conditioning, so cooling and appliances, then it's a question of ownership. How many air conditioners or how many refrigerators, televisions are owned on average by the household? And then how does this ownership evolve based on increasing income? So again, an S-curve, rapidly increasing at a certain point and then starting to slow down as ownership saturates. Now, just a note here on cooling, we could also say that floor space per household is an important variable, because if we're trying to cool a much larger household with 1 air conditioner, then we're going to be having a higher energy service demand. So we can certainly look at both variables, firstly the ownership rate, and then also if we have an increasing number of meters squared per household, that will also increase the floor space, the energy service demand, sorry. So in cases like this, we can look at having 2 activity variables that both combined can help us to understand the evolution of energy service demand. Now, to move on, I wanted to come back to the fact that sometimes we want to bring in additional variables to help us describe the trends. So if we look on the left-hand figure, the x-axis here is just GNI per capita. So it's an income proxy, essentially. So we're taking our income variable and we're using this to describe the number of units per household. But we can see that the curve is quite cramped. It's really not an easily defined S-curve. And that's because in the first, let's say, $5,000 of GNI per capita, there's a huge amount of people that suddenly buy refrigerators. And it's all happening very rapidly, and perhaps economic variables such as GNI per capita are not the perfect variable to understand what's happening in this first part of the curve. But now if we turn to the right-hand side figure, then we can we use here a discriminant criterion. So this is basically saying it's a variable without a unit, which is just an indicator that combines several proxies. So it's combining GNI per capita, so it's taking the economic variable, but we're also bringing in information on the electrification rate within the country and the urbanization rate. Because when we start plotting this data, we clearly see that not only does the economic variable influence ownership, but so does electrification rate and urbanization. Because obviously we're not going to buy a refrigerator if we do not have access to electricity. So despite the fact that we might have an income, if without electricity, there's no point buying a refrigerator. So this is, it seems evident, but obviously it becomes very important when we start translating it into these curves, and we can see this flat period at the beginning for those that still don't have access to electricity, despite the fact that they might have an income. And likewise, the data shows that with higher levels of urbanization, we also have higher levels of refrigerator ownership. And so we bring in these 3 different variables that describe so an energy access trend, an economic trend, and a geographical trend, and bring that information together to build this discriminant criterion, which then helps us to get a much more clearly defined S-curve, which is then more useful in understanding in the future with a given a value for energy access, for income, and for urbanization, what might we expect in terms of ownership. So this is multivariate analysis and multivariate regression, as opposed to the earlier examples which were shown, which were using a single variable, so GDP per capita in those instances. Okay, now let's run through the principles of multivariate analysis for be using many or several economic variables, population variables, or other interesting variables for which we have information to describe the evolution of activity variables. So the first point here is to look at the data that we do have. So taking the data we have on, say, if we're interested in refrigeration ownership, looking at the available data on refrigeration ownership, selecting a set of these data points which seem like a good, clean trend, and then trying to match these data points with available variable data on, say, GNI per capita, GNI per, or GNI absolute values, electrification rates, weather data perhaps, or any other variables that might be available. And then what we can do is plot all these variables together on a chart. And so, for instance, we'll have our variables on the y-axis on refrigeration ownership, and then we'll be plotting that on the x-axis against lots of different variables again and again to try and understand, is there a relationship between that variable refrigeration ownership and the variable that we're putting on the x-axis. And so what we can do, what we achieve by doing this, is we identify the most important variables that seem to have some sort of relationship between this variable and refrigeration ownership. And then we can partition the data into similarities, or based on what the data is actually describing. So for instance, if I take GDP per capita or GNI per capita, they're very similar data points. And so within this multivariate process, there's no point having data points that overlap and describe very similar trends. So even though both GNI per capita and GDP per capita are very useful variables that can both be used to describe the evolution of my activity variable, I'm not going to put them both into this multivariate analysis because they are describing the same things. However, if we look at a variable such as electricity access, then that is removed from GDP per capita and describing a different set of trends, and therefore we would put that in another class, and it would be very useful then to have variables from different classes, for instance, 2 or 3 variables from 2 or 3 different classes, and bring these together to then feed into to establish the best combination of these descriptive variables that can be used to describe our activity variable. So once we have the 3 or the 2 variables that we've chosen, then we want to use a certain type of multivariate regression to understand what the best combination of these variables is to best describe this activity variable trend. So for us, we use canonical variate analysis. So that's something that that you can look up and try and understand the processes involved. Or there's many other multivariate regression techniques that can be used to combine several variables to deliver one discriminant criteria. So one variable that combines all this information and then can be used for us to plot and understand the evolution of the activity variable. So that's then step 5. Once we have this relationship defined, then we can use our projections of, say, electricity access rates, of urbanization, of GDP per capita, feed all this information in, calculate our discriminant criteria, then take the discriminant criteria, put it into our curve equation, so our S-curve equation in this case, and then that will give us a forecast of the ownership of the activity variable. Now, the final point I want to make before I pass on again here is what we do with tracking data and how do we project the variables that interest us when we do not have the available historical data. So to take a step back, the first thing we do is we bring all the data that we do have together for all the countries that interest us. And then what we'll do, we'll divide the countries into different classes based on the type of, I guess, the category of the country. And so, for instance, we would bring countries together that have similar economic contexts, that have similar climatic and population growth contexts. So here on the left, we can see we've put countries, so country A, B, and C into different classes. And so we have several different classes for countries across the world. But for instance, if you're looking just at the African region, it might be pertinent just to have one class and to not bother about defining different classes. Now, once we've done that classification by class, then we need to look at the data availability for each country within each class. So for instance, if we take the example of country A, then country A is a country that is well informed in terms of data. So we have historical data available for many years for the activity variable that interests us. So it could be household occupancy, it could be refrigeration ownership rates, it could be floor area per average household. So here we have the information we need historically to be able to build the curve, build a robust equation that then can be used for the projections. However, for many countries, this unfortunately isn't the case. We do not have this data available. So for many countries, we find ourselves in the position of country B. So that means we're poorly informed. We might only have a couple of data points. So there might be a data point from a survey that's taken place only once, or maybe 5 years ago and 10 years before that. And so that means that we don't have sufficient data available to build a robust and reliable curve, so an S-curve equation, for example, and then to be able to use this S-curve equation to project activity variables into the future. And so what we do in this case is we use the curve that was described by all the countries for which we do have data. So we take the average curve of all the countries in class 3. So for instance, if we put all the data for ownership of refrigerators in class 3 together in one figure, and then we use that to describe, to build an S-curve, and we have the equation for that S-curve, we can then use that S-curve equation for all countries that find themselves in the position of country B. But we shouldn't forget that for country B, we do have 1 or 2 data points. So what we'll do is we'll then shift the curve up or down to make sure that the curve is running through the most recent historical data point that we have available. So that's a way of ensuring that for us, we can use these curves to describe the trends for the 1 or 2 data points we do have, and to backfill the missing historical data, as well as understanding how these activity variables will evolve in the future. The final situation is the situation of country C. So this is a country for which we have no data at all for activity variables for the end use that interests us. So in this case, we have no other options. All we can do is take the average curve of class 3, so the average of all the countries within this class. And so that means country C will just be described by the average throughout, because we don't have any data points to be able to shift and run through those data points. And so we go straight through to the projections of the activity variables using obviously the economic variables that are specific to country C, but using the S-curve or the inverse curve equation, that is the average of all the countries in class 3. So this is a very important point on how to find the data, and then what to do with the data, and what to do, very importantly, when we don't have the data, all the data that we need to build these curves, and therefore to project the activity variables. And just a point to note on data, so obviously there's many different sources available for countries across the world, but in many African countries, it can be quite difficult to find this sort of data. So at the International Energy Agency, we've often looked to surveys such as the surveys conducted by USAID, and we can find these surveys online, the DHS surveys, and often there is information within those surveys that can be used to help us in this modeling process. Alternatively, there can be specific literature on a specific country based on surveys conducted within that country, or based on academic work. But basically, the first step certainly is to look for the data that does exist for the end users that interest us most, and to contact or reach out to as many people as you can to try and get the best data and ensure that you start with the strongest foundation.
So back to our presentation. So you heard from Tim and Ariane those activity structure performance structuring of our modeling work, as well as the drivers and how to manage those large amounts of data, how to benchmark with other countries with data available from other regions or from the past, so that we can build on them. Now I would like to first take any question you may have on what was just presented, or here for any reaction, any comments, and then I will have some more questions for you in the live polls. I'm pausing for a second for you to be able to write questions. So first question from Mr. Ibrahim Sulu. Why is agriculture categorized under buildings? So indeed, this is more of a statistical treatment and typology definition. We usually break down the energy end use sectors under industry, transport, and building plus others. And in that case, building will include residential, so private housing, plus services like buildings used for banks, for enterprises, etc. This can also include agriculture, indeed, and other end use sectors. So it's more of an international standard. Sometimes you can find agriculture as separate and sometimes inside. What is always very important is to make sure that whenever you communicate on data or whenever you read some data, you have the metadata available, in other words, the definition, so that if you read a number, you can know the exact scope, you can know that this is a sum of residential per service plus agriculture plus other, if that is the case. And also, another reason for that is that when you look globally, if you had to really come up with three main sectors: industry, transport, and residential service agriculture together, would be three balanced categories. I have a hand raised from Hamad Hamin, so I give you the floor. Hello.
Hello, good morning.
Good morning. Yeah, please go ahead.
Yeah, I have two questions. I need clarification on the two definitions. You made mention of GNI. I want to know more about it and the canonical variate analysis. I want more explanation on this, please. Hello?
Sorry, yeah.
Hello?
Yeah, so thank you for those questions. GNI is for growth national income. So it's
Okay.
depending on the methodology, on the data available. Sometimes we look at GDP, which is the most common indicator for income and for wealth produced at the level of a country. GNI
Yeah.
is adopting a slightly different approach, really looking at what is produced in country. So you can have a big difference for countries who rely a lot, for example, on trade versus the wealth which would be created in country, on territory. So this,
Okay.
but mostly it's really an macroeconomic indicator.
Okay.
On your
That's
second question, can you come again on
about
that?
this, the canonical variate analysis.
Okay, for that, if you don't mind, I don't want to mislead you on that, so I will ask my colleague Tim, who will join in 30 minutes for the second Q&A to answer to you and illustrate how he's been using that.
Okay, thank you very much.
Please bear with us on that. Thank you.
Okay, no problem.
Okay. Maybe one additional thought on agriculture, just to mention that as always, what we need to understand clearly an energy system and then to be able to make modeling and projections are good data and good allocation of data. So for example, a common challenge we face is that you may have agriculture which would include activity which are not always formal, with households which do a bit of agriculture, or small-scale farmers who would use some equipment and machine. But for all those users, if they have, for example, a small equipment, a small pump, a small vehicle for agriculture, the fuel they will put in that vehicle or equipment might not be easy to identify as something going to agriculture, because maybe you have someone who will go to the pump station, to the gas station, and just fill a jerry can of diesel or of gasoline and use it not for mobility and transportation, but use it for an agriculture purpose. But it will be very difficult to have this information when looking at the data. And so when building the energy balance of the country, often there is a lot of energy and there is a lot of oil products which are absorbed under transport because they are sold at a gas station and they are not clearly identified as agriculture. Okay, I have, I think, Mr. Ibrahim Sulu who raised the hand too, so I'm giving you the floor.
Good morning.
Good morning.
Yes, please, I want to share my thoughts on the issue, on the question I asked. Yes, 2 years ago, we conducted a survey on fuel wood consumption in the residential sector. So that we find out that some agricultural businesses at low scale level are mixed with energy consumption at household level. So in that perspective, putting agriculture under building may be acceptable. But I think agro industry, where larger machines are used, can we still put that one under building? Do you understand the point I'm making?
Yes, on the fact that for small agriculture businesses, they might use electricity which come from a unique meter, for example, which is the same for the residential needs like lighting, powering appliances, and for using like a water pump, for example, in the agricultural need.
Or the small rice processing, like parboiling of rice, all these type of things, they still do this. In Nigeria, we still do this one at the level of household. But when we are talking of mass production of agricultural products, I don't think we can put it's better we put this one under industry than buildings.
Yeah, so this is indeed a very difficult challenge, and thanks for sharing this experience. I was mentioning for oil products, so that it's hard to differentiate if a liter of gasoline is used for a car or two-wheeler or for a small tractor or agriculture machine. And as you just mentioned, the same goes for electricity. It's hard to differentiate under a unique meter if the watt hour, the electron is used for lighting the rooms or for using a water pump, for example. This relates to the fact that a lot of small agriculture businesses are not formal or would not have separate business accounts, for example. So I think my guess on that, and I'm not the statistics expert, but I will ask to Zakia and other colleagues, is that some surveys, as the one you might have done, can give good ways to can give some indication on what share of electricity or of oil products that are usually considered under transport or under residential shall be reallocated to agriculture to reflect better the sector. But I will definitely ask more guidance from the statistics team on that.
Okay, thank you.
Now, thanks for your sharing. Okay, so back on the methodology and a bit the theory on doing those modeling, I just want to ask you two quick polling questions. Okay, so let's imagine in an exercise like the one we will work on Excel later on. So if you know how much energy an air conditioning unit needs, then if you want to get an idea of the total energy demand in the country for cooling needs, what would be the most important parameter to take into account? Would that be the size of houses, like floor space in square meters? Would that be the number of households? Would that be the number of units, number of air conditioner per household? And I'm sorry, I'm seeing that the pictures are not displayed in a good way. Okay, so you're mostly voting for the number of units per household. No good or right answer here. What's for sure is that in our reasoning and our approach, we can indeed think at the household level, looking for one average household, how many units we have. We know how much energy one unit will consume. And then, of course, we will multiply by the number of households in the country to get our numbers at the country level. Floor space can also be a very interesting proxy to see to get idea of how many units an household will have, because if people live in very small houses, maybe one AC unit or one fan would be sufficient to meet the needs for cooling. On the contrary, if people live in very wide places, they might need more than one AC unit. But it can also be a question of income. How many equipments can people afford? And then it might be about other indicators. So another question now, looking at water heating. So if we know how much a water heater consumes in terms of energy, what would be the most important parameter, again, to estimate total demand? And again, you can think that we have like multiplier factors, like the number of households to move from the thinking at the scale of a household to the entire country. We have really the activity variable, and we have proxy which would give us good indications on how the demand for service would evolve. Okay, so you're mostly voting for household occupancy. Indeed, floor space is not the right indicator to get an idea of how much hot water people want. The right indicator is how many people are there in a family, because hot water is directly correlated to the number of people living in the house. And of course, we will need number of households to bring that number to the scale of the country. So thank you for your answers. I'm coming back to the presentation. And now we'll see more how to move from those econometric analysis you have seen with all our inverse curves or S-shaped curves. So those to make the link between drivers and the need for energy. So we'll look now, once we know how much energy, how much service people want, how will that translate into our final energy needs? So how many kilowatt hours will be needed, how many liters of oil products for moving people, etc., etc.
Once we have determined past and projected activity variables and service demand intensity, the total energy service demand, or useful energy, can be computed. For this, we can rely on end-use intensity, which is derived from our projections of activity drivers, as well as other data coming from our database, like the historic energy demand by fuel and end users, historic and projected temperatures. So we usually use heating degree days and cooling degree days, or historical technology market share and efficiency. For instance, with all this information, we can compute the energy intensity per square meter for space heating. Once obtained the total projected service demand, we can now reflect on which technologies will meet the demand. So for each year of the projection, we can compute the total energy service demand that needs to be satisfied by new equipment, by accounting for new incremental demand and considering the retirement of existing technologies. So of course, in later years of the projection, we also have to take into account the retirement of technologies that were added by our model. So how do we do this? For this, we need to have a detailed stock and with the lifetime, we can determine the remaining stock for each year of our projection, and finally, we can compute the service demand to be met with new sales. So the sales of new equipment need therefore to replace previous equipment and to meet new demand for energy services. So you can see that the lifetime of equipment and its age distribution can play an important role in the capability of the system to renew the overall technology stock. In countries with burgeoning energy demand, such as in developing countries, the share of replacing old infrastructure and technologies is more limited, while its weight is more important in advanced economies. Now we have to determine which technologies will meet the service demand. The technology and fuel choice depends on a variety of elements, and first of all on the available technologies for each subsector in each market considered. That's why we have an important database with all technologies available in each subsector. So for instance, you can look at the cooling subsector and you can see the different types of air conditioner that are in the model. The choice of technology depends on various parameters. The available potential of renewable resources can play a very important role, as well as several energy policies such as energy efficiency standards. In the world energy model, we rely mainly on a cost-based approach to determine which technologies will be installed. For this, we need to compute the cost associated to each technology, which includes the investment cost as well as the operation cost. For instance, for an air conditioner, we must take into account the price of this AC, but also the price of electricity that will be consumed by this technology. In our model, we assume that the technology share will be proportional to 1 divided by the specific cost of this technology. This least cost approach is often the most used criterion to select the technologies, but it's also important to consider boundaries to reflect market failures, behavioral patterns, and energy policies. For instance, we can set a minimum target for heat pump to be installed if we consider that energy policies are pushing the development. Here you have an example of the projections we made for various lighting technologies. On the left, you have the evolution of efficiencies, and on the right, the evolution of the market share of the LED. So with this information, we'll be able to compute the main outputs of the model. So you can see that estimates of historical efficiencies and performances of equipment and possible future evolutions are key parameters to make reliable estimates. That's why technology partnership, sharing information, and continuous interaction with the energy industry are really crucial elements to achieve it. As said before, once the technology choice is determined for each subsector for each projection year, together with the market share, efficiency, and fuel of use, the final energy demand can be computed, as well as the related CO2 emissions and the investments that are needed for new equipment additions.
In the last part of this building's energy demand modeling session, I would like to provide several examples of the results of our modeling, specifically the results of our modeling applied to the Africa context, and use these results to reinforce the importance of efficiency gains and understanding the impacts of improving efficiency and changing technologies on energy demand. So these are some of the results that we can then communicate to policymakers to reinforce certain messages and the importance of taking steps and putting in place policies to achieve energy objectives. So here we've taken an example from the International Energy Agency's World Energy Outlook Special Report on Africa, published in 2019. So looking at electricity demand from household appliances in the year 2040 under two different scenarios. Now, if we look at the left part of the figure, we can see that under a scenario where the current and announced policies are enacted and economic growth follows an expected trajectory as announced by the International Monetary Fund, then we could see electricity demand across Africa for these uses, for residential uses, increasing to around 350 or close to 400 terawatt hours. However, if we pass to a scenario where economic growth in Africa is much more rapid, so economic growth is in line with the expectations for African countries, and we also have energy access, so universal access to electricity and to clean cooking, which is achieved by 2030, so in line with the Sustainable Development Goals, then we see a much more rapid growth in energy service demand. So obviously, if we come back to the activity variable story and the bottom-up modeling process, then higher economic activity means higher average household incomes. This then translates to greater floor area on average per household, much higher household ownership of appliances such as refrigerators, televisions, washing machines, and higher household ownership of cooling equipment such as air conditioners. So if we just added to the system the same equipment that was being used in the step scenario, then we would have a huge increase in electricity demand. So going from around 350 terawatt hours to over 1,000 terawatt hours. So this obviously has very important implications for power systems and for the costs needed to increase generation capacity, increase transmission capacity, and then for energy bills, electricity bills for consumers. But what we want to show here is that by improving the efficiency of the appliances that are added, we can drastically reduce the impact of all these additional appliances. So that means that we can have a big increase in demand for energy services and so in quality of life because people have more appliances, but we've limited the impact on the energy system. So that's through greater efficiency. And so if we look at the right-hand side of the figure, we can see the very important differences in the ownership variables for different types of appliances averaged across Africa. So we can see that we have significant growth already in the steps, especially in appliances such as televisions and refrigerators, but also in air conditioners, although they do remain at a much lower base. However, if we look at the Africa case, then this growth in ownership really does explode. So obviously this is important. It's people getting access to services, but via the modeling, we understand that as we put in place more efficient technologies, so thanks to policies, then we can limit the impact on energy systems of this increase in energy demand, energy service demand. So to be able to do this sort of analysis, we also need to have the modeling in place, but we need to understand what policies are in place today and what are the efficiencies of existing equipment and equipment being sold. For instance, we'll need to know how efficient are the air conditioners being sold today and what policies are in place that would impact the efficiency of these air conditioners. So that provides us with a baseline, and we can also look at how the policies and the policy change over the last years has impacted the energy intensity of these end users. So here is just an example where both heating and cooling policies have been tracked, and we can look at the building stock and the useful energy demand in terms of understanding which part of that energy demand is covered by policies or not covered by policies. And then based on that, we can understand how stringent is the average coverage across the building stock. And so what we want to see is that this stringency improvement really brings down the energy intensity of meeting demand for services such as cooling and heating. And if we take the example of water heating, then here we're looking at the evolution of energy demand in 3 different scenarios. So the first scenario, the RTS, is a scenario similar to STEP. So here we're just looking at the policies that are in place and the policies that have been announced, whereas the 2 scenarios to the right are more ambitious scenarios that meet climate objectives, so a 2-degree scenario and a below 2-degree scenario. So what we see here is just pure outputs of our model when we impose the constraints of saying we need to reduce emissions in line with a certain scenario, so 2 degrees or beyond 2 degrees, then that means we need to see a big change in the fuel mix. And so this is obviously bottom up. It's coming from us saying we need to allocate a renewable technology as opposed to a fossil fuel fired technology. And these are the evolutions of the energy mix that then result. So it's these kind of results that can provide a visual communication of what the modeling is doing and then help us to bring together key messages and key numbers to communicate to the policymakers who can then act on the information coming from the model. And one final slide here is very specific to Africa and specific to cooling, to again underline the importance of increasing efficiency. So Africa's cooling needs, as many of us know, are much higher than most other places in the rest of the world. Many locations across Africa have cooling needs that are an order of magnitude higher than in countries such as France or Italy. And these cooling needs also dwarf major cooling demand centers of China and the United States today. And we see that almost 700 million Africans today live in areas where the average daily temperature exceeds 25 degrees. And average temperatures are often 1 to 2 degrees higher again in cities. And as Africa's population increasingly urbanizes, cooling needs will further grow. By 2040, the number of Africans living in hot areas approaches 1.2 billion people. As populations expand, especially in cities, and average temperatures increase with climate change. High cooling needs today and higher cooling needs tomorrow contrast with some of the lowest levels of air conditioner ownership in any region. Averaging today only 6 units, so 6 air conditioners on average per 100 households. Now, obviously, wealthier countries across the continent, such as Morocco, Algeria, and Tunisia, have higher ownership rates that can be up to 3 times the average of the African continent itself, while less affluent countries with often much higher cooling needs have ownership levels that are only half the African average or less. So as a consequence of this low average ownership of cooling needs, electricity demand for cooling today is very, very low in Africa. But the potential for future growth is strong. Ownership of cooling devices sees an important increase in our Africa case in response to these higher average incomes I described earlier and rates of access to electricity. So we reach in 2040 an average of 25 units per 100 households, but this is still well below the global average today. Ownership of fans increases further, but fans obviously have a lesser impact on electricity demand. So if we focus on electricity demand from air conditioners, then we can see that electricity demand in the residential sector across Africa for this end use could grow to well over 200 terawatt hours by 2040. So that is just a huge increase in demand that would have major implications for power systems, especially because of the fact that air conditioning electricity demand is often concentrated in certain hours of the day, so difficult to manage. But the importance here is to use the building energy demand modeling to understand that if we change the efficiency of these air conditioners, then we have the potential to cut this future growth in half. So we can reduce costs for the power system, reduce costs for the consumer, and reduce emissions. So here, this is again the messaging using the model to understand if we change certain variables, such as putting in place a policy which improves air conditioner efficiency, what are the results that we could expect?
Okay, so you've seen again some of the findings from this modeling work, especially on cooling, and that gives a good transition with the Excel exercise we had on this topic. So I hope you could have the opportunity to look at the Excel exercise, to try to make the calculation yourself, or even to look at the answers. I will share with you my screen so that we can go through a bit of the questions and trying to go through all the reasoning of it. So here again, we try to translate and to illustrate concretely all that was said by Tim and Ariane, putting you in the shoes of someone working maybe at the Ministry of Power, and to whom the question is, okay, we all know that first, global warming or global climate change is in certain regions increasing the temperature, so we expect people to long for more cooling services. We also know that with the development of incomes, with more socioeconomic development, people will equip themselves with more appliances, including cooling devices. So we all hear that there will be strong rise in the need for cooling, but the question is by how much? How much more electricity shall we be able to generate if we want to match this demand? And how with this evolution will take place over time. So these are a bit the overall question we want to answer. And to do that, we'll take all the steps that were discussed in the presentation. Sorry, I ask you a second. Okay, now you should be able to see my screen. So you were given a simplified model where we have historical data as well as projections. So we have socioeconomic drivers as usual, GDP per capita and population. For them, we have both historical and projections that would come from International Monetary Fund or from the Ministry of Finance, for example. And then we have data which relate to our topic of residential cooling. So number of households, number of AC units in the country, service demand intensity, and total electricity demand for cooling needs. So we know how these parameters have evolved in the past 2 decades, and we want to make projections. So I won't go question by question, but just showing you more the reasoning steps. You were asked, I think, first so starting with the drivers, what we want to look at is how many AC units, how many equipments shall we expect to find per household in the future. And then, as we will be able to easily deduct the number of households, we will be able to make projections on the total fleet of equipment, the total number of AC units. So we have, in the year 2000, we had 500,000 air conditioners. Today we have 1.4 millions, and we'll try as a first step to estimate how many there will be in the future. So to do that, we'll look mostly at the scale of one household and try to understand how many AC units there are today per household and how this would evolve. So moving directly to the solution one, AC units per household. We have the number of AC units in the country and the number of households. So we just divide it. When it comes to making projections of AC units per household, so here there are different ways of doing it. Again, we could just project what the past growth rate was. What we'll try to do here is a bit different. We'll look at how the GDP per capita is evolving and how the number of AC units per household has been evolving too. So this is what we call an econometric approach, and we just put here on this line the evolution of GDP per capita. So this is historical data plus projections that we know, again, provided by Ministry of Finance, for example, and we'll try to deduct number of AC units per household. So we've just expressed those two parameters, one as a function of the other one. So you can see on the horizontal axis GDP per capita, and on the vertical axis, number of air conditioner per household. The yellow dots are the historical data we have. So what we have just done here is based on this line to create with Excel a trend line. And then depending on what your formula looks like, we could choose different type of trend line options. Here we've taken linear. So this is the blue small dots line that you can see. And with this line comes a formula of y equals a factor a multiplied by x plus a factor, a constant b. And Excel automatically calculates and gives you what a amounts and what b amounts. So we have the parameters for this formula. If we want to make a projection which is similar to what happened in the past, we can just continue the formula. We know how GDP per capita will evolve, so we can deduct based on this function how number of units per household will evolve in the future. So this was one step to deduct future level of equipment per household. Then number of people per household. We have also historical data, and we could maybe find some data from statistics agency looking at demographic trends. We could make projections based on how things have evolved over the past 2 decades. Here, we have tried to do, again, an econometric approach and looking at the relation between GDP per capita and number of people per household. And here the idea is that if you look at a large number of countries with similar characteristics and a large amount of data from past trends, you can establish relation between how rich people are and how many people are there in a household. And this is what we just do here. So that's exactly the same as what we did. We enter GDP per capita historical and projected data. And we enter for the historical data the number of people per household. And we create a function of one parameter as a function of the other one. Here, we don't have a linear curve, but we have an inverse curve. And again, we can ask Excel to add a trend line. It will not really be linear. Maybe it's more polynomial. Maybe it's more exponential. So we can try several, and we will get likewise a formula, a mathematical formula, where we have y, so the number of people per household, expressed as a function of x, which is GDP per capita. And since we know how GDP per capita, or x, will evolve in the future, we can just make the calculation to project. Here, the calculation is a bit more complex because you see there are 3 parameters, A, B, C, and C is a more mathematical calculation. But using, for example, Excel solver functionality, you can automatically get your answers. So doing that, we have made our own estimation of both how many air conditioner will there be per household and how many people will there be per household. We can deduct how many households will be in the country, and multiplying those parameters, we can deduct how many AC units we expect. And here we see that it's much more accurate than if we had just made a projection of number of AC units in the country linearly, because in the year 2000 we had 500,000, in 2018 1.4, and we find that we would have 2.7 million air conditioner in the country by the end of the decade. This was first step. Then we have to look at energy service demand. In other words, people have air conditioner, Okay, but how much will they want to use it? And here again, we have historical data that were provided. What we can do here is just to project future evolution based on historical rate. And here we have calculated the growth rate between 2018 and 2010, which is at 3.5%, and we will apply the same rate. So just making that there is a 3.5 annual increase year after year by the end of the decade. And total service demand can be deducted because we know how many equipments we have. We know how much kilowatt hour one equipment requires, so we can deduct the total service demand, which is getting closer to 1 terawatt hour of service. This is not final energy yet, because we know how much cooling needs, and we know it's expressed in terawatt hour, but now we need to see the equipments that will meet those needs. And we have taken the assumption that we have 3 technologies. It could be air conditioner of low quality, of middle quality, and of high quality. And each have different level of efficiency that are given to you. It's asked to calculate the average efficiency, and this will be based on the total service demand divided by the total electricity demand that was given to. So we get our average level of efficiency. We need to work on the technology allocation, or in other words, what's the market share of each technology. And this is where we can make projections, taking some assumptions. You were said that technology number 3 was not yet available so far, but it starts entering the market in 2019, and there is a strong policy to bring it to 7.5% of market share by 2030. So this is the target for 2030, and we can linearly attribute the value starting from 0 in 2018. Then technology number 2, you were told that we expect it to increase by 1% every year based on the current levels. And technology number 3 is just taking the remaining so that we have 100%. So we know technology market share, we know technology efficiency, we can deduct the compound average of the average efficiency of the total fleet of equipment. And from there, as we know total service demand and we know average efficiency, we can deduct the electricity demand for cooling. So you can answer very simply to that question that today 0.15 terawatt hour of electricity is demanded for residential cooling needs. Based on this exercise, we expect by the end of the decade this electricity demand to rise to 0.35 terawatt hour. And as we've done in the past, this is just one model taking assumptions. And what is very interesting is to develop sensitivities analysis. And here we can develop different cases, saying that, for example, our base case was assuming that the demand for service would increase at the same rate as it increased in the past, so 3.5% every year. But it could be increasing at a higher rate of 4%. Then we would have this orange curve in terms of total electricity demand. But we could also have, on the other hand, some policies to make to promote more efficient technologies. And for example, our AC, our air conditioner of the technology number 3, which is much more efficient, could be promoted more by policymakers and could reach 20% rather than 7.5% market share by 2030. And in that case, the average fleet itself would be more efficient and we would reduce significantly the demand for electricity. So I'm stopping here on the Excel exercise. And now happy to take any question you would have on the exercise itself, or on the presentation, and on what you heard from Tim and from Ariane. So as usual, you have the Q&A box, and you can also raise your hand. I have noted a question from Mr. Hamad Amin to Tim, and I will invite you to just as soon as Tim is joining us, I will invite you to ask your question again. So I know the exercise was a bit fast, but you have all the detailed answers in the booklet, so you can look at any answer. Hi, team.
Hello. Yep. Nice to see you all. Thanks, Arno.
Thanks for joining us, and I know it's very late where you are in Australia, but we really appreciate your connecting and answering to some questions from our group of participants from Nigeria.
With pleasure.
So we had a question from Mr. Ahmad Amin on the first part of the presentation. Mr. Amin, I will give you again the floor. It was a question related to some methodological work. If you could ask again, I think Tim would be able to answer.
Okay. Mr. Tim, good morning, or is it good afternoon? Hello.
Hello. Good evening. Yeah.
Yeah. Okay.
Good morning to you.
Okay. Morning. I have a question on this canonical variate analysis. So it's like I need more explanation about that.
Sure. So what we're trying to do in that step there is to look at several variables and try and understand the best combination of those variables that allows us to project forward the ownership rates of specific equipment or other variables that we're interested in. And so canonical analysis is just a type of statistical analysis that enables to take several inputs, such as the electrification rate of a country, or the gross national income of a country, or things like the urbanization rate, and to combine all these variables together. And so in terms of the actual methodology for that analysis, then I would suggest canonical analysis is one type of multivariate regression technique. But otherwise, you can find several techniques if you just sort of, I guess, Googling multivariate regressions, and the best way to do this sort of analysis is probably the best way to go. Here at the IEA, we have a certain methodology using this canonical analysis, but any multivariate regression analysis would achieve the same objectives, really.
Okay, thank you very much. And I have another question to do with the Excel. Will I have access to a YouTube on how to go for the mathematical manipulations on the Excel spreadsheet?
Yes, so the Excel is detailing the you would have the formula on if you go to each cell. Maybe one technical point I quickly mention is the solver add-in, which is a very smart and very useful Excel nice functionality where you can ask Excel to optimize itself some calculation. So in that example, we ask Excel to make itself the calculation of finding what our variables are in the what our constant values are in the formula. You may remember we had a formula like y equal a multiplied by x plus b, and just asking Excel to find itself what a and b will be, just defining this kind of defining the formula. This is something very powerful and useful. But apart from that, we are mostly doing some calculation of applying a growth rate or calculating a compound average growth rate. If you know the value like energy demand in 2010 and in 2019, and you want to know what was the annual growth rate year after year, you just have a calculation to make. And well, I often forget and relearn the formula. You just need to write it down somewhere. But these are indeed some formula you can find to help the calculation.
Like the first formula you mentioned is about straight line. The straight line equation, y is equals to a factor plus b x. That one is to do with straight line equations. I know about that one.
And you'll find as well that in Excel, when you plot the data that you're interested in, so this data could be the gross national income against the, say, refrigeration ownership or television ownership, then you can use Excel to plot a trend line. And then for that trend line, you can choose different types of equations. So you can choose this straight line, y equals ax plus b, or you can choose a polynomial or logarithmic. And so based on all those different options, Excel will provide you a different formula and show you which formula, which line is the most accurate in matching the data that you have.
Yeah. My other question now is, you made mention to where I will repair. What is the cost that I will use? What will I type under YouTube for that Excel? You mentioned one version of the Excel that will be easier. Can you mention it?
Yes, we were referring to the solver tool as well as some formula. If you look at the handbook with all the exercises, in the last pages of the annex, you will find some information on useful Excel formula. But just sharing the screen again.
My problem is I don't have that book because I had Mr. Arnold referring to it. Or is it this lecture notes I have been downloading from YouTube?
So you should have received a link for a Google Drive folder with all the presentation as well as the handbook with exercises and the Excel version. So all of you should be able to access all this material. If you've not, please let me know. I will be happy to share again the link.
I don't have it. Maybe you just have to help me send the link so that I can just link and continue doing it.
Okay, I let maybe Tim answer these one question that was asked, and in the meantime, I will paste in the chat of this group the link to the drive.
Okay, no problem. Thank you very much.
So, thank you. In the chat, we have a question on, can these variables be classified into exogenous and endogenous categories for the modeling? So within the modeling, we do a first step, which is what you've seen in this presentation. The first step being to project the service demand and the ownership of the different types of appliances and the area. So for us, this is an exogenous step in the modeling because we start with exogenous data, which is, for instance, the GNI per capita or urbanization rate. So these are data points that come from outside of our agency because they're not related to energy. And so we use United Nations data, government data, or other projections. That's exogenous. We then do a first step where we do all this regression analysis to then be able to project that the ownership data. And so for us, we consider that as exogenous. That doesn't change in the model. That's separate to the different scenarios. And then we do the modeling, taking these exogenous variables, and some of the endogenous variables will be things like the technology allocation, the investment needs, and then finally the energy demand and emissions related to that. So for us, just to summarize again, most of the ownership variables are exogenous, and then it's the energy demand, investment, technology allocation variables, which are endogenous. Now, just one final point, there's one exception to this. Sometimes we can take, for instance, air conditioner or fan ownership as an endogenous variable, because we will make that ownership change based on the level or the change of climate. So if we're in a scenario that has higher global warming, higher increases in global average temperatures, then we'll have higher ownership projections for cooling equipment. So I hope that answers the question, and please feel free to post if you need more clarification.
Thanks, Tim, for that very clear answer. We still have 5 minutes, so if you have any other question, please feel free to ask or to raise your hand.
I don't know if there's we have a question from Ahmad Amin.
Yeah, Mr.
Hello.
Amin again. Yeah, we can hear you.
Yeah, I want to ask on this solar thermal electricity generation in Nigeria. Do you have any tangible data on that? Because in 2017, I was able to go to University of Hull and did my master's in the renewable energy. And I concentrated much on solar power in Nigeria. I don't know how far your IEA has gone on this generation of electricity by thermal solar system. I need more explanation from that. That is my question, please.
Thank you.
Go for it, Arno. Yeah.
Yeah, just mentioning that you may have heard last week from our statistical colleagues that we aim to collect all the data from all the technologies. So for sure, we are looking at solar thermal and trying to work with each country. I guess for Nigeria, it shall be the Federal Ministry of Power looking at the level of production for solar thermal. And we reflect those numbers in the data we issue. We also look at the different technologies to understand how they work, the level of efficiencies, the service they can meet, and the prospect. But for that, Tim, I'm sure you would have more to share.
Sure. So I guess there's a difference depending on whether we're looking at solar thermal from a utility perspective, such as for generating electricity. So for example, similar to the solar thermal, the concentrating solar thermal plants that we see in Morocco, or if we're talking about solar thermal, say at a household level, where it is mostly used directly for things like water heating. And so as Arno mentioned, in terms of data, wherever available, we're taking these statistics. But on our side, it's more about looking forward and trying to understand, well, what is the potential for say, something like solar thermal in buildings in Nigeria in terms of how much sunshine, how much irradiation, and the average temperatures, and then using that potential and information on costs and efficiencies to try and understand what part solar thermal could play in the energy mix going forward. And so obviously, if there's policies or subsidies that can make such technologies cheaper, then they'll have a much more favorable future.
Thanks, Tim, for that answer. We have a hand raised. Maybe this will be the last question we will take. So, Mr. Abubakar Ali Dabshima, I think you should be able to speak.
Thank you very much. I am Engineer Abubakar Ali Dabshima. I am from Ministry of Power, Deputy Director in the Renewable Energy Department. I just want to, talk in respect of the last speaker, the comment you just answered on this solar thermal. It is very interesting. The last, person that asked this question, if he can meet us in the department, we actually, want to explore more on how to go about solar thermal in Nigeria. And we have some reservations. Since he has his study abroad on that aspect, please, we would like him, if he can meet us in the ministry, so that we can discuss further on that while you are gathering your data, so that we can all collaborate and, have a very good insight on this solar thermal. To us, it's also a key, and we've been looking for, expert like this, which he has done his master's in solar thermal abroad. It's good to collaborate with him and actually to know our, the direction we want to take, and also based on the study he had, because on our vision 30-30-30, there is a projection where every year we're supposed to achieve solar thermal, but because of less data and also some complication from our own end that we've envisaged, we could not be able to, make progress. So with him talking with us and also with AIE, I think we can make a way progress on that. Thank you very much, please.
Thank you, Mr. Ali Dabshima. We will make sure that you can have the contacts of Mr. Hamad Amin, and very pleased to facilitate this work. So I think we're running out of time. I'd like to thank you very, very much for your participation today, for your interest on what we have presented, and big thanks to you, Tim, for your presentation, and also for coming and joining very late Australia time this question and answer section.
Thanks very much. All the best, everybody.
Have a good day, everyone, and we'll meet again tomorrow to discuss the power sector. Have a good day and see you tomorrow.